Now we're going to do the last topic in this chapter, that is the principle of inclusion-exclusion. You can also think of this as a generalization of the sum principle that we did a long time ago. Recall that the sum principle was about when you had to make two choices, when you had to make one choice and you had two options, then you add the two different options together. But you add them when the two options are separate. Now we're going to see what to do when the two options overlap with each other and there is something that is common to both the options. This is best explained by example. So let's say I have a set of non-negative integers from 1 to 10. And I ask the question, how many elements of S are either odd or divisible by 4? So let's do odd first. I'm just going to count by hand. There is no theory going on here. So let's say there's 1 here, 3, 5, 7, 9. So for the first thing, the answer is 5. How many of them are divisible by 4? For this, I get 4 and 8. So for the second thing, the answer is 2. And if you look at the total list, the total answer is 7. So all I'm doing is I'm adding these two together. This is the sum principle. If I have two choices and the two choices have nothing in common, I just add them. Now the second, I'm going to twist this question slightly. Suppose I ask something similar, but now I ask for odd and elements or elements that are less than 4. Okay, so either, again, let's count. So I have 1, 3, 5, 7, 9. Again, I have 5 elements which are odd. And how many are less than 4? Now I have 1, 2, and 3. 3. And if I just naively add them, I get 8. But now let's see if there are 8 of them. I have 1, 2, 3, 4, 5, 6. There are only 6 of them. So I'm overcounting. Now, why is there an overcounting happening? Because there are some elements which belong to both of these things. That is the element 1 and the element 3 is in both, it's both odd and it is less than 4. And so there is a double counting happening. And so I will subtract 2. And this 2 is to do with the double counting. And I'll get 6. And that is the number I have. So the procedure is I count the different choices and then I subtract the ones that are counted twice. And then from this, and that's where the name inclusion-exclusion come from. You can think of the first piece as saying include all the choices separately and then exclude the double counted ones. And that's why inclusion-exclusion. And this can be made more precise using the language of sets from the previous chapter. So let's say I have 2 sets A and B. And this time the sets overlap. And I ask what is the size of A union B? Well, what will be the size of A union B? I can say, well, it's the size of A plus the size of B. So that is like the previous example where I'm saying take all the elements of A, include all the elements of A, and include all the elements of B. But if I count it this way, then you see that the elements in the middle are getting counted twice. And so I subtract that from my total count. And that is exactly A intersection B. Because the colors are a little unclear, let me put an arrow. And the first part you can think of as inclusion. And the second part you can think of as exclusion. I'll say that the principle of inclusion-exclusion is the beginning of the theory of combinatorics. Combinatorics is a whole branch in itself. When you start learning the subject, you just learn tricks, which have nothing to do with theory. You just see different ways of counting things in some very fancy ways. But now with principle of inclusion-exclusion, this is something a little more systematic and organized, and you can in fact do a lot of abstract stuff with this. So let me just give you an example of how abstract this can become. So say now you have 3 different sets and your goal is again the same. You're trying to count the number of elements in the union. And the power of inclusion exclusion is it tells you the answer without too much overthinking. The derivation is in the book, but honestly, the derivation in this case is not that important. The important thing is to remember the formula. And the formula is include, exclude, include, exclude, include, exclude, and so on. What do I mean by that? First, I will do just this. That's the inclusion part. But now things are getting double counted, so I'll subtract. Okay, so I subtract the things that are in the intersection to remove the double counting. But the things that were in the triple intersection, unfortunately, those have gotten removed many times. And so to fix that, I'll include them again. So let me shade these regions. I won't shade A, B, C. You know what A, B, C are. They are the big sets. Now, what are the intersections? The intersections are these. And you can see that when I try to subtract the intersection, the piece in the middle gets subtracted multiple times. And that's not what we want. And so this thing gets added to the final count. And that's the last piece I'm adding. You start with inclusion, then you have an exclusion, and then you have inclusion again. And the way they differ is you take different sets and then take different intersections of sets and then take different triple intersections of sets. And if you had 4, then the next step would be take quadruple intersections of sets, and you can do this for all lengths. Maybe one day when you do more abstract computer science, you will find that this is an extremely powerful theorem. You can write programs based on this simple principle because it tells you exactly how to count elements in sets without any tricks or ambiguity.